Today we are going over homogeneous linear equations. Now, an equation is homogeneous if its right-hand side is equal to 0. So for example, y double prime plus y prime plus y is equal to 0 is a homogeneous linear differential equation. This is different than the other homogeneous definition we've covered, and in this course from now on we're going to be using this definition of homogeneous where the right hand side is equal to 0. And here is how you'd find the solution to the homogeneous linear differential equation. So first you'd find your auxiliary equation. And to do that, you're basically going to treat each degree of derivative and you're going to bring it down as a power. So this just becomes m squared plus m plus 1. And the reason why this y here is 1 is because you can think of it as y to the 0th derivative. And since it's y to the 0th derivative, you don't bring an m down here because it's m to the 0. And therefore, you just bring the constant down, which is just 1. Another example would look like 9y triple prime plus 9y prime plus y is equal to 0. And you'd bring it down like 9m cubed plus 9m plus 1 is equal to 0. And your second step is to solve for m. So for example, if you get an auxiliary equation that looks like this, you can factor this into m plus 1 and m minus 1, in which you would get m is equal to negative 1 and 1. The third step is to classify your solutions. So there are three distinct cases. One, which is your real roots, in which you would get y is equal to a constant times e to your first root plus another constant times e to your second root, and it goes on and on for all of your real roots. The second scenario is where you have repeated roots. Now, if you have repeated roots, your solution would look something like this. Y is equal to c1 e to the mx plus c2x e to the mx. And the reason you're multiplying by an x each time is that you're going to want your terms to be linearly independent. So if you were to have, for example, a third solution, then it would be added c3x squared because you're multiplying by an x each time, e to the mx. And your third case are complex roots. This would be if you were to get a quadratic that can be factored into complex conjugates, so alpha plus or minus beta I. So an example of a complex root would be 5 plus or minus 3i. So your 5 would be your alpha and your 3 would be your beta. And the solution for this is your constant times cosine of beta x plus another constant times sine of beta x, and it's all multiplied by e to the alpha x.